بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولا و نعم النصیر. Okay, last session we talked about multivariable control, and we started the advanced topics in control structure of robotic manipulators. We started with the general nonlinear and multivariable dynamics of a robot. Of course, this is not very sophisticated, but it is. And somehow we have the Christoffel matrix, we have the gravity term, we have the mass matrix, and the second order dynamic equation, which is multivariable in terms of vector base and also nonlinear in terms of the nonlinear Christoffel terms, especially Christoffel terms that we have. And it is also configuration dependent. All the matrices are variable to Q or sometimes to Q dot. This means that we have a configuration dependent model here. This means that the robot, the dynamics of robot changes depending on which location we are working. And usually the robots are, the controller are tuned for a particular configuration. For example, my arm is working very well here, not when I am touching this way, because this is becoming quite singular, and it is not very good to do that. And usually we don't do that. If we would like to work here, I prefer to use my left hand instead of my right hand, and that's why we have two hands basically. But the problem comes to the picture that we have some sort of issues in this here. All right. So we started with this matrices, and I recall the mass matrix, which is basically composed of two parts, the original mass matrix and the part that comes from the electric motors and the actuator side and the gearboxes, that we have some gear ratios at each part, mentioning again that we have a trade-off between nonlinear effect of the robot or the dynamic of the robot and linear effect of the actuators, which comes into the picture in this particular case. And when this is dominant, we can just go before and don't use any multivariable control, just use simple PD control or PID controller that we have talked before. And if this is dominant, maybe we can also neglect this part, but usually a combination of these two or a trade-off between these two dynamics comes into the picture, and we cannot completely neglect all the nonlinear dynamic terms or rely on the linear equation. So if this is the case, we have a general dynamic equation here, and what we showed is that in a multivariable control, I would like to go through the computed torque method, which is the most important part here. And again, we talk about it last session, but I would like to give some more indication and some details about that. We see that in this case, we have a controller which is composed of two parts. One part is the nonlinear part and the multivariable part, which includes all the matrices, the dynamic matrices that we have, M, ME, BE, C, G, the terms that has been derived from the dynamic equation. And this is an inner loop, we call it an inner loop. We use that to somehow linearize the system to get rid of the dynamic terms. If we know exactly the value of a mass matrix, and we know if this mass matrix is quite accurate in terms of the structure and also in terms of the parameters that we are using in both cases, that will result into, we call it feedback linearization loop, that will cause this dynamic equation, which has these nonlinear terms, to be vanishing in, as you see, to be vanishing in the closed loop system. If we put this control effort by control, if we put this control effort here, as you see, many parameters here, like C, like B, like G, will be cancelled out, will be linearized, or will be disappearing from the closed loop system because of this inner loop controller that we are using. So this inner loop controller, or the feedback linearizing part, is very, very important, since we are reducing the nonlinear multivariable model to some sort of linear part. And again, why we are using in this ME, we extract that ahead before, and this one we put it in the feedback, we put this one in the feed forward. This has a chronicle or historical evolvement. It was not like that, but after a few trial, this is the final computed torque method, or in the inverse dynamic or feedback linearizing control that we are using. And then the main reason that we are extracting ME from this part, we didn't put it here, because we didn't want to have the feedback of acceleration feedback in the loop. Here, as you see, we have only velocity in position feedback in this loop, and the acceleration comes only from the desired value of the acceleration, which is very smooth usually, and it is known before that. Anyways, this is one part of the controller, and don't forget the outer loop. This is also very, very significantly important. Don't think that the feedback linearization is doing everything and all the job, and the performance is coming from this part. No, this is not true. More than half of the weight of the controller is still on the linear part. We are using a PD controller here as a linear part, but this could be a more general term like a PID, or even a robust H infinity controller. It could be a different method we can use in here. We go with the basic line in here, and see that if we have a PD controller, as you see in here, a PD in a matrix form, a diagonal PD form, as you see, everything is bolded. This means that we have matrices here, not singular value, not single value or scalar value gains. We have matrices here, and then if we put both of them together, we have the feedback linearization term and also the PD term here, and the acceleration coming in here. If we put it in the dynamics of the system, we will see that by considering having full knowledge of the system, these many terms, nonlinear terms, will cancel out, and we reduce to a very, very effective, very desired second order system. Of course, again, multivariable, not error is 6x1 vector. A multivariable vector that can be very clearly tuned by the matrices Kp and Kd, and it is configuration independent. It depends if these are all of this assumption of full information knowledge is satisfied. So by this second order equation, you can use your linear control background to design the PD controller in here, or to tune it through the system. So if we summarize everything all together, we say that inverse dynamic controller or computed torque controller, the PD gain can be much more easily be tuned because we have this configuration independency through this feedback linearization. Actually, we have linearized and somehow put the system from a multivariable into a number of single variable controller, and we can use the decentralized or diagonal PD matrices to control the system. So we can have very good tunable response by tuning the PD gains here, or using a PID if you require to have zero steady state error to non-vanishing disturbance. If the disturbance is vanishing, the steady state becomes to zero, and this is usually not the case. We usually don't have zero vanishing, and not because of this tau d. This term, the term gravity term that we are using, if this is not completely cancelled, if these are not equal to each other, which is usually the case, if only a small value remains in the gravity term, that means that we didn't have the opportunity to cancel all the gravity terms, then this acts like a disturbance, a non-vanishing disturbance, and from our previous result in PD controllers, you see that the steady state error becomes not zero, but will be limited to some positive value that we can have in here. But if we don't have that, of course, we can have the steady state error become to zero. Again, the dynamic configuration is independent of the model to the configuration, and the PD gain selection and tuning would be much easier. But this method is a base control method, very popular, very used. We don't use feed forward that much. This is much better than feed forward because of the positive values that we consider here compared to the feed forward. But it is the base one. We put something on top of that. And you see at the becoming in the next slides, we can make that a bit more advanced, but usually the foundation is this inverse dynamic control or the computed torque method. But now look at the weak point, and we will try to work out this weak point and to see if we can have some sort of issues regarding this problem. Note that full information requirement never holds practically. It is impossible to have exact value of the mass matrix, C matrix, G matrix, B matrix to be known for a robot. So if you do a very well sophisticated identification process even, and do a lot of work on the calibration of the robot, you know that all the least square method, all the method that we are using for identification and calibration have a small, at least a small remaining error because there are some approximate method to find the parameters. And you saw in last chapter that changing the configuration and also changing the frequency of the input will change the dynamic of the system. And usually we have some uncertainty, some unknown knowledge here. We cannot get rid of that. And this is the most important difficulty to use an IDC controller, because it is much closely related to the model of the system. It is a model-based controller. And a model-based controller, the main important problem, it is not robust. and since we don't know the exact model and parameter of the system in practice, we have always some problem. But this problem, as you see, so we don't go to this very, very fantastic equation that we have here. This is very ideal. Actually, this fantastic equation will be perturbed by some terms that is the difference of the values that we can get, the nominal values, from the true value. And the true value, we don't know it. This is not that something that it is available somewhere. We don't know it. To the best of our knowledge, we can get the nominal value of that, which we displayed with the hat variable. And this, if we can consider the error in mass matrix, the error in B matrix, the error in C matrix, which is also very important, and the error in the gravity matrix, and if there are some disturbance input, they can all of them can be seen as a disturbance, configuration dependent, state dependent disturbance acting on the system. And here you see the powerful power of the outer loop controller that can somehow reduce the effect of disturbances. As you see, this part becomes much more important, and you should spend a lot of time on that accurate tuning of this PD controller, not only to have the tracking error as you require in the second order case, to have zeta or omega and design as you wish, to reject the disturbance. And this is the magic of feedback that we are using. The feedback, the most important and essential characteristic of feedback is that it can optimize multiple criteria, or we can have the tracking error, and at the same time we can have also some disturbance rejection variable, and also the sensitivity of the system can be reduced. The sensitivity of the closed loop system can be reduced by tuning high gains for the controller, and these issues are very, very important indeed. Of course, this is only true if these errors are not very large. If they are large or varying, then this disturbance becomes quite heavy and effective, and you cannot reduce it by a simple PD controller. But if you do your best to find accurate value for M, B, C, and G, then you can assume that, okay, we had 100% nonlinear terms, we have reduced 90% of that, we have cancelled 90% of that, not all of that, but 90% of that, and we are now with a 10% nonlinear term coming into the picture, so we can assume that the PD controller can work well. In practice, in my experience, usually this is working quite well, and if you don't need super high accuracies at the response, this will work well. And it is important to have the G term quite well determined, since this is a non-vanishing disturbance, and you know that a non-vanishing disturbance cannot be compensated by a PD controller. This is why we go to the next part. The next part is partial linearization. Partial linearization is somehow the idea that we have used before. We have the controller, we would like to use a computed torque controller, but since it is very difficult to find the C matrix, you need to remember that the Christoffel term, you will learn that in this assignment that is due to next Sunday, you will see that finding the Christoffel matrix is usually difficult, and it is very important not to use that. And it is particular of interest because of the properties of m dot minus 2c. We can use a much more simpler controller. Instead of using all these terms, we can use, this is the least expensive or difficult or complicated controller that you should do. This is the minimum requirement that you have to be using in the control part. We will see that to have steady state error, good steady state error. Here, as you see, we don't use, look at here, we don't use this term, we don't use this term, nothing here, nothing here. This is just all, we just use the PD controller and the gravity term. The gravity term is, we use the impartial linear. You see, we use much simpler controller, a PD controller, plus the gravity term. And we can show that. If we know the gravity term quite well, if G hat is equal to G, then we have very, very effective response and performance coming from this system. Now, this needs some analysis, and this analysis is based on Lyapunov second method that many of you are familiar with that. So we say, assume that there is no disturbance and the gravity is also well known. We have full information here, but we are not using M matrix, we are not using C matrix at all, and we use the controller coming to the system. If we put this tau instead in the term tau, and if we consider G is equal to G hat, G and G hat system becomes still nonlinear and multivariable. We have M dot, we have B and C Q dot available since we have not touched them, and we have the PD controller. Now, is this good enough? What will happen to our steady state error to a step input, for example? What will happen to the stability of the system? Is the system stable, become stable? What would be the criteria for the stability? Stability is very important for the robotic manipulator to be working in an environment that the human is also there. So usually the security and the confidence that we have, we should analyze the stability of the system. You see that we cannot analyze the stability of this system through Rod-Horowitz or, for example, root locus or the linear method like Nyquist criterion because this is a multivariable and nonlinear system. It is not a linear system. There is no Laplace transform defined here. We cannot use any of the very, very effective and important techniques that we have used and we have learned in the linear control theory in here. The way that we are using is the Lyapunov method. And the Lyapunov method is, if I explain it very short, we use a Lyapunov function, which is energy-based usually. We use a positive definite Lyapunov scalar function. We call the Lyapunov function with V, and we take the derivative of that. If this is positive definite, and derivative of that is negative definite, if this is always positive and the derivative of that is always negative, then the system becomes stable. This is the intuition that if the energy of the system is positive, an energy dot, the decay of energy or the change of energy is always negative. We have a decaying energy system. The energy of the system is reducing, so this will result into a stable system. And this is basically the Lyapunov second method or the Lyapunov direct method to show the asymptotic stability of the system. So for a constant, this can be, the Lyapunov stability can be used only for steady state variable, not for transient. We cannot talk about transient here with Lyapunov. We need other means to do that. But the Lyapunov method will show you what will happen at the end at the steady state values where all the systems are constant. We consider that we have a desired trajectory. The Q is some constant, like a step, a unit step or a non-unit step. So we don't have any Q dot desired here to be able to use the Lyapunov method or the steady state analysis for that. And now we go with designing the Lyapunov function from the physics or the properties of the system. We use the Lyapunov function as the total energy of the system. In this case is the kinetic energy. We have the kinetic energy before in Lagrange, the Q dot, ME Q dot, this is the kinetic energy, and the potential energy. Since we have a PD controller for the closed loop system, this acts like a spring, a virtual spring in the system. So we have also the potential energy here, which is 1/2 EQ KP EQ. Of course, you can use any positive definite one, but here this positive definite system Lyapunov function comes from the energy of the system. So to analyze the stability, we should take the derivative of V. If we take the derivative and notice that this V is scalar, the result, as you see, this is not bold. This is scalar. This one should be also not bold. This should be scalar. But these parts are vector and matrix manipulation. So you should get the right derivative of that. And if you get the derivative of that, you can see that, for example, this quadratic term will result into two terms. The first term is with the second derivative of Q dot, and since this is symmetric, usually we have this 1/2 gone. So we have this one. And also the second derivative comes from the second term, comes from the derivative of M. We know that M is configuration dependent, so there is an M dot available here. So this part will result, the derivative of this part will result into these two, and notice that we consider for a constant input, not for a variable input. Otherwise, this doesn't hold. And this term will result into EQ dot KPEQ or EQ KPEQ dot. Doesn't really matter which one you're using because these are symmetric, basically. And also you don't have any 1/2 thing here. So V dot has three terms, and if we can show that V dot is always negative, is always decaying, it means that the energy system is always decaying, and that's the result into the stability of system. And this can be shown quite easily. Just look at the MEQ double dot. MEQ double dot, as you see, can be replaced by this equation. This is the closed loop. MEQ double dot is KPEQ minus this term. So we can put it here, substitute MEQ double dot, as you see in here, put it in here and simplify. We substitute, and we notice also, since Q dot D is equal to 0, E dot Q, which was Q desired minus Q dot, Q desired dot is equal to 0, so EQ dot is equal to minus Q dot. So if we put this term, as you see, these 1, 2, 3, 4 terms here, 1, 2, 3, 4 terms here, and the rest we will keep it here, you will see that these 4 terms, the red terms comes into, these 2 terms can be cancelled out for any robotic manipulators because of the skew symmetricity property of the system. You see that M dot E minus 2C we discussed it before in Lagrange in the last chapter that m dot minus 2c is equal to, it is a skew symmetric matrix, and this means that this term becomes 0. So if you see m dot minus 2c, we have a 1/2 here, so you just multiply it by 2. As you see here, you see these two terms become 0. So the big problem that we have with the C, with so many terms, just cancelled out because of this property of the dynamic equation, which holds for all the robotic manipulator. And this is not required really to put the C in the controller. Of course, if you put that, the performance might become better. But in terms of the stability, it doesn't really change because this m dot minus 2c is equal to 0. And also the green one, you see we have a positive term here, a negative term here, and the negative term comes from this term, as we showed, and we put that just E dot Q equal to minus Q dot. As you see, these two terms also will cancel each other. So this term, this long equation becomes into a small equation, which is quite fantastic. It is a negative equation. So V dot is equal to minus Q dot KD plus BEQ dot. Technically speaking, this is negative semi-definite because this is a function of only Q dot, doesn't have the value of Q, but we can use the LaSalle theorem to show that this results into asymptotic stability of the system quite well. I didn't go through all the nonlinear details here because you are not that familiar with all details, but you know, I will claim that, and you believe me, that this will result into a steady state error equal to 0. So this means this control structure, which is very simple, much more simpler than this. We don't have C term, we don't have B term, we don't have ME term. We don't need to cancel these three terms. We just need to cancel the gravity term. And you know that the gravity, if you don't cancel the gravity term, you have a non-vanishing disturbance. A non-vanishing disturbance doesn't go to 0 steady state error. You don't have asymptotic stability property in here. So the only term that is very important is to find the G term. And the G term was the simplest part of the dynamic equation to be found. And of course, we can do some experiment to find the values of G gravity term quite accurately, as we discussed in the dynamic term. So finally, by this variable, we can say that we can use partial feedback linearization. We don't need to use the full feedback linearization. Any question? So as you see, I'm going very slow here with a lot of details talking, just for you to understand all the details. Is there any question?
May I ask a question?
Moin has a question. Very good, Moin. You can ask and then Zahra.
Hello, excuse me. There's a level in nonlinear control that you mentioned when there's an exponential function and we can the bounded input would result in stability. Can we prove that this equation, on the left side of this equation, the error has exponential response, so the left-hand side of the equation acts like an input, so the stability proved by Barbalov theorem. Can we say that or not? Excuse me, it was explained very.
You can ask in Farsi, don't worry.
Okay. یه قضیه که کنترل غیر خطی بود. شما فرمودین که اگر ما پاسخمون چیز باشه، به صورت نمایی باشه، ورودی اگر باندد باشه به پایداری منتهی میشه. الان اینجا ما ارورمون پاسخش خطی، پاسخش نماییه. میتونیم بگیم که
کجا نماییه؟ کجا میگه نماییه؟
خب چیز دیمودا دیفرانسیلش پاسخش نماییه دیگه.
غیر خطی.
بله
غیر خطی ها، سیدات داره، سی داره.
نه الان شما الان اسلاید قبلی شما اگه بیارین
ما اینجا یه ترم سیدات داریم.
نه الان شما سمت راست اگر ملاحظه بفرمایید ایداد داریم و یکی
درسته.
این پاسخش نماییه دیگه.
این ور چی؟
این ور به صورت کلا سمت چپ و به صورت یه اینپوت در نظر بگیریم.
نمیشه.
دیستربنس در نظر بگیریم.
نمیشه. این درست نیست. یعنی این تکنیکال نیست، یعنی نیازی نیست. یعنی با شما نیازی نیست از باربالات استفاده کنید. البته نه اینکه بگم نمیشه، میشه، ولی یک کمی با دیتیل. توجه کن که این استیت دیپندنته. اگه این استیت دیپندنت نبود شما میتونستید به عنوان اینپوت بگیرید، اما این استیت دیپندنته. وقتی معادلاتت این ورش استیت دیپندنته نمیتونی فرض بکنی این ورش پایداره. اگه اون فرض می‌کردی پایداری که پایدار بود دیگه اصلا برای چی میخوای پایداری رو اثبات کنی؟ اگه فرض می‌کنی باوندده، خب باوندده دیگه اصلا برای چی می‌خوای لیاپونوف یا باربالات استفاده کنی؟
نمیدونیم باوندده، نمیتونیم اون ور اثبات کنیم.
نمیتونیم. بله نمیتونیم. باید اول اثبات کنیم که باوندده و نیازی نیست ما از باربالات استفاده کنیم. باربالات برای زمانیه که شما متغیرهای یعنی نان اتونوموس سیستمتون زمانی داره تغییر میکنه. اینجا اصلا نیازی نیست. چرا؟ چون سیستمتون بر اساس استیت تغییر میکنه ولی بر اساس زمان به صورت اکسپلیسیت تغییر نمیکنه. شما به راحتی با همین ساختار ساده، با همین تابع لیاپونوف میتونید پایداری رو اثبات بکنید و نیازی نیست برید تو فضاهای پیچیده تر. در واقع
خیلی ممنون.
موفق باشید. زهرا، any question?
Yes. I just was wondering why KP does not affect on the rate of Lyapunov.
Again, we don't have your voice quite well. Why KP?
Yeah, in the rate of Lyapunov function.
Okay.
In next slide, I think.
KP is not here. Not
Yes.
seen in here. Why it should be seen in here?
I'm not saying it should be here, but well.
The important is that it shouldn't be seen in here. You see that KP is cancelled out, you know, because we have used a particular Lyapunov function, which is from the kinetic energy and the potential energy. This is the potential energy. So in the derivative of the V, the potential energy doesn't come into the picture. What comes into the derivative, the damping terms, comes into the picture, and you see the damping terms are actually available here. Both BE, which was a dynamic damping of the system from the linear part of the system, and the controller damping. The KD is the damping of the system. We should never have the kinetic energy coming into the picture. If it comes here, then we have some trouble. Then it is not very easy to simplify the system. It is like a magic, you know. It is very simple. That's why we can teach that in an introductory course for even bachelor student. Is there anyone who don't understand what we are doing here? It is very simple. We use the energy of the system, take the derivative becomes negative, so the system is stable. That's all. And it should be like that. Otherwise, this doesn't mean that KP doesn't matter in the system. Yeah, it matters a lot, but it doesn't contribute in the stability. It contributes in the transient response, in the power of the system, in how the dynamic equation is evolving. But what will cause the stability is these damping terms.
Okay.
These damping terms. If you somehow have some negative damping, for example, if KD is not positive, it is negative, So you lose your stability, completely your stability, and we never do that, of course. We don't have any PD controller that the D terms is negative, it is always positive.
Right. And by the way, how we tune the KD and KP?
Like what we have done before. Of course, this is also a very good question. We didn't provide you with simulations here. And of course, you can look into my book, in my parallel robotic book, not in the serial robotic. I should provide some simulation to you. I will provide during the assignment in your project. What we're doing, you know, by Lyapunov stability, we just ensure that we are not in trouble. We are not unstable. Doesn't mean that we are very good in performance. Still, the PD gain shall be tuned quite well. So you use, depending on how much effort you can give to the system. You use this dynamic equation. You can consider this dynamic equation. The relation between Kp and Kd, you use somehow to have a zeta equal to 0.707. You have a very Butterworth relation, or very good relation in terms of the transient. So you keep the ratio between Kp and Kd somehow to have the zeta assigned to a desired value that you wish, and then you increase the gain, both of them. You increase the gain somehow to get to the saturation point, how much torque you can apply to the system. So you increase the gain as much as you can, not very high, as much as you can. The limit is coming from the actuator saturation. And you keep the ratio between Kp and Kd somehow to have the transient response working well with a very small overshoot. If you want like to have faster response, you can have, you know, some smaller zeta, you have some oscillation. But usually in robotic, we don't need that oscillation. We go with the zeta equal to 0.707, and then just by tuning that in a simulation, you put this controller in the simulation, you change the gain and see the response. You change the gain and see the response the same way that you tune in the controller. It is harder to tune the controller when you are using partial feedback linearization rather than a full feedback linearization. Of course, if you have a full knowledge of the system, the controller tuning becomes much simpler. But you are using much simpler controller. The controller is almost linear, almost. The only term that you are adding is a gravity term, and the gravity is compensated by the controller.
Thank you so much.
Very well. So let me just go a step forward, just one single step, and don't talk too much. This is the cornerstone of what we are talking, and this analysis is what we should be learning to do in this course. I will go to the next one. What will happen? This is also very advanced, believe me, but I will give it very simple word. There is another way to use the computed torque method or inverse dynamic, but instead of using the first topology that we have in the beginning of the course, the joint control, we can go in the task space. You know that. Let me show you. When we are in the task space, we know that the robot shall work in the task space. So the desired trajectory shall be always in task space. And we have the measurement Q's. We don't have the measurement of X, so we can use the measurement of Q in the forward kinematic to find the X. So it is much better and much practical to use the outer loop controller in the task space if you would like to do very accurate positioning. You are doing, for example, some seam welding, something that is really required to be well done in the task space of the robot. it is very difficult to do that if we would like to use the feedback linearization all in task space, because the dynamic equation that we have was in Q, not in X, and to change that in X, it is a lot of trouble. So what I propose, again here, from very many different topologies that are there, I prefer to do that. Of course, this is also given in the Spang book. You can read through that. I will keep the inner loop. I don't change anything in the feedback linearization part. We can use either full feedback linearization or partial feedback linearization if you wish. I'm going with the full feedback linearization since this is our baseline. But I change the outer loop to a task space. And to just understand that, you should quite very well know this characteristic for a simple IDC in joint space. You see that if you have a joint space, you have AAQ here, something which was like acceleration term or a torque term. You see that Q dot, double dot comes and adds to the tau PD, and this gives you the AQ term. This we index it by Q. This means that this is in the task space. Now, we can change that into a Q to be in joint space. We can change that into the task space. How we can do that? We just use, we would like to, instead of having Q or Q double dot in our outer loop, we would like to have our X double dot. And this X double dot can be found from the Jacobian. Again, the importance of Jacobian come into the picture here. A robot without Jacobian, knowing nothing without the Jacobian, don't know anything about it. And that's why in your midterm exam, we discuss a lot about the Jacobian. Still, in your final exam, we will ask you to find some Jacobian. Jacobian is very important. And you see that the X dot is related, Q dot is related to X by Jacobian. If you take a derivative of that, X double dot is related to Q double dot by a Jacobian plus a Jacobian dot, since you are differentiating this. And this is very golden rule. And now, if you would like to find the Q double dot, like a Q double dot from this equation, you will see that Q double dot, that we call it AQ double dot, is J minus 1Q X double dot minus this. And we put this one AX minus this. Now we have a relation between this value that we had in regular term, the AQ term, in a regular IDC, to what we require to do in our task space. Instead of AQ, we would like to put the AQ here. But we would like to find AX and then find the AQ. AX and AQ can be defined by this way, by the inverse equation that we are using here, minus J dot Q dot J minus 1, and we put this one into the picture. Now, the AX, this outer loop is all designed in the task space. This means that we need the acceleration in the task space to be fed here. We need the desired trajectory in the task space to come here. We need the error to be found in the task space. And the PD controller shall be designed in the task space. Everything in the task space, totally different from what we have done before. As you see, we have a tau here. We had a tau here. Now we have an F in here since we are in the task space. And we add these two together, we find the X, and then we convert it to here. We use this equation in here for conversion in here, rather than conversion in here. This is much more simpler and better in practice. In many books, they use just simple inverse dynamic, all in task space. They change all the M, B, C, G terms. I don't recommend it at all for the robotic for serial manipulators here. For parallel manipulator, it is quite possible to do that, but for serial manipulator, we don't touch the inner loop. We use all what we have in the dynamic term. We just change this golden rule. We use the AX in the task space and then change it into AQ. As you see here, if you put in here, then the error space, if error dynamic, if we have full information, of course, the error dynamics will result in the task space. So you can design in X, Y, Z, in the direction that you are really, the robot is working. You can tune the gains to have more accuracy in X desired term, in the Y direction. Something that is not possible to do in the joint space. If you change the K1, K2, K3, Kp in the joint space, you are changing the accuracy of the rotation of the variables that you have. But here, when you change or tune the Kd and Kp here, they are in task space, you are tuning the X direction of the end effector, the Y direction of the end effector, and also the rotation, the screw rotation that we have at the end effector. This is called different names has been given to here. They called operational controller to this one as well. In some books and in some references, but I prefer to just use the computed torque or inverse dynamic in task space. And we note that we don't change the control structure that much. At least the inner loop is unchanged. We are using all the dynamic equation that we have found, all the manipulation that we have done there, identification, calibration, everything that we have done so far. We use all of that knowledge here and only change this part. Use this golden rule to find AX from AQ, and the outer loop gains, PD gains, are tuned based on the task space. I would like to ask you in your project and in your assignment that will given, the last assignment, the project that will given, to use both of them, use the task space and also the joint space in the simulation to be done. If there is any question, I will stop here and then hopefully go to the robust and adaptive controller in the next two sessions. In one session, I will talk about the robust control, and in the other one, I will talk about adaptive control.
I have a question.
Sure.
Go to the previous slide.
Again, you speak a bit that we have your voice better, and then...
could you please go to the previous slide?
Yeah.
Does it matter where we consider the disturbance torque trajectory? Like, since here we are calculating inverse of Jacobian, is it better to consider disturbance as F in the task space, or it doesn't matter?
It really doesn't matter because, I put tau D here because I'm using the dynamics in the joint space. Everything is in joint space, so tau D is coming in here. If we have a FD, so we know that the F to tau is related to a Jacobian transpose. You know that. So you can change one to the other by a Jacobian transpose. Notice that if you are in the inner loop, we are always in the joint space, so we use all the characteristic of the joint space dynamics here, that we have the tau D here. In the outer loop, we are using the task space, so we can we have to use all the characteristic of the task space that we are using, which are usually the formulation that we are giving here in terms of the controller and the forward kinematics and the issues that we are working in here. And you look at if you look at this is very, very similar to our third topology, if you don't remind me, let me just go back to the first slide. If you remember here, this is our control topology 1. Up to here, we are using this one. Then we go to control topology 3. This particular case that we are talking is usually like using a third topology, since we are using a Q here and an X here. And if you have to replace tau to F, you can always use a Jacobian transpose in here.
And in practice, what are main sources of torque disturbance?
They are in task space. Mm-hmm. They are in task space. Depending if you have some disturbances on your links, on your joints, then it is on the joint space. But usually we have some friction, at the task space, or the payload will be changing. You pick something up, so the robot payload will be changed. We don't call that a disturbance, the payload. We distinguish that. Usually, even in the simulation, you change the payload, you change the end effector mass, and this is quite possible. You are picking something up, and then see what will be changing. If you change the mass, so your dynamic is changing, and so M and M hat is not equal to each other anymore. We shall use some robust and adaptive controller for that.
Okay, thank you so much. Thank you.
You're welcome. Thank you very much. There is another question, yes?
Yes. May you go back to the last slide that you put up?
This one?
Yes, the like that you referred the golden rule. I think it is very hard to find the derivative of Jacobian. It is very complicated.
Who said that?
Because when I wanted to do that myself, it was very complicated to find the derivative of Jacobian. It has a lot of terms.
You're doing it by hand.
Yes.
I told you in the beginning of the class, don't do it by hand.
Okay.
Never do it by hand.
But for example, for analytical derivation of a formula.
Why analytical?
Okay.
Who said it's analytical?
Mm-hmm.
You can do it very effective. And this is very important when I'm telling you that this is about 20 years experience,
Yes.
Yeah, of course, if you want to do it by hand, you can do it. I don't mind. But go and do it.
I don't mean by hand, for example, by my hand. I said, for example, even by solving by Maple, the matrix would be very huge, and sometimes Maple has trouble to find it.
No, this is not the case. For Jacobian, this is not the case. If you do it by Maple, this is correct, but you don't put the Maple one here. Since you are, what we are doing, we have a Q. We have at each iteration, we have the Q and X available. We have the Q and X available. So in here, you have a Jacobian, which is a function of Q. We have a Jacobian dot, which is a function of Q. The Jacobian dot is a function of Q, and you have the Q available. This is very large in Maple if you put sine, cosine, everything in analytical. But if you assign the Q here, it becomes a very simple matrix. So you do it because you are doing it in the loop. We are doing it in the feedback loop. We cannot do it offline. We are doing it online, but never do it by hand, first of all. Second, if you find it by Maple or if you cannot find it by Maple or by hand, you cannot do it. Of course. But it is not that difficult, believe me. Even for a very sophisticated 6th degree of freedom manipulator, you can do it by hand, by Maple or by symbolic. And you don't use the symbolic formulation in the loop. We just assign it sub value, put the values in here, then it becomes a very simple Jacobian matrix, and it is working well. And there are a lot of problems in some papers. You can see they have very, very difficulties to do that. I understand that you are doing well here. Your question is very well, but the issue is just do it this mean. I think it is very important for you to read our latest paper. We have a latest paper working on the dynamics of the system and also the regressor form for serial manipulator and also for parallel manipulator using virtual work approach. And in there, we give also some formulation and some simulation for very, very difficult, for very, very sophisticated robotic arms. We can simplify that and also effectively calculate it in real time.
Perfect. And can I add another question?
Sure.
Most in the major of cases,
just ask in Farsi. It is much.
معمولا از سرو موتور اگه برای ربات‌های سریال استفاده کنیم، سرو موتورها یه PID خودشون درون خودشون دارن. ولی خب همین دیگه. الان اینجا ما اگر بهتره که تو فضای تسک طراحی کنترل
اصلا کافیه یه دونه PID کنترل روی سرو موتور داریم. شما یه دونه مثلا فرض کنید موتور چیز خریدی، داینامیک سل خیلی مشهوره تو ایران، بعد یه PID هم بستی روش، وقت روش لود بذاری رو تسک بیس این کار میکنه؟ نه. برو ببین کار میکنه یا نه.
همون دیگه منم
اصلا مناسب نیست. بله یه موقعی شما میخوای یه چیز کوچیکی رو باز جابجا کنی، خب معلومه کار میکنه، ولی یه موقع شما لود داری و این وریبل لود حتما باید بری رو تورک موتور کار. همون داینامیک سل های خوب در واقع 2 تا مود دارن و ما یه دونه تورک دارن. وقتی اومدی رو تورک یعنی شما اون تورکی که میخوای، البته اونم باز خوب کار نمیکنه اگه خیلی بهش لود وارد بکنی، ولی میاد رو تورک. اگه بیای رو ولاسیتی کار کنی، ببین اون PID میگه که برو رو ولاسیتی. آیا اگر من بار زیادی وزن کردم، فرض کن من اومدم موتور رو قفل کردم، دستمو گرفتم، ربات نداشتم حرکت کنم، میتونه اون ولاسیتی که گفتی بره؟ خب نمیتونه بره، معلومه نمیتونه بره. بنابراین اونجا گیر میکنه. چه اتفاقی میفته شما نمیبینی، یعنی شما بهش کامند میدی بره یه جای دیگه میره، نمیبینی دیستربنس ها، نان ونیشینگ دیستربنس ها. ولی اگه رو تورک بدی، این چون تورک هنوز به اون مقدار واقعی نرسیده، این تلاششو میکنه، ممکنه موتور بسوزه، ممکنه یه جا گیر کنه موتور بسوزه، این امکانش هست. البته اونجا هم کلمپ میکنه، اجازه نمیده انجام بشه. ولی در واقع شما توی فضایی که ما داریم کار میکنیم، من نمیگم اون فضا انجام پذیر نیست. یه دونه یادم هم اومد که اصطلاح ریسرچ دادیم، من باز نکردم رو سایت، ریسرچ دادیم که اگه خواستین رو ولاسیتی کار کنین چه ایشیو هایی داره. ایشیو اصلیش اینه که شما یه فیدبک داخلی داری اونجا، ولی این فیدبک داخلی فقط برای دیستربنس های کوچیک، فقط برای پهنای باند کوچیک کار میکنه. اگه شما لود زیادی، ربات درگیر با محیط بشه، اگر لود موتورتون زیاد بشه، لود یعنی بار یا بازاتون بزرگ بشه، اصلا کار نمیکنه، اصلا خوب کار نمیکنه. حتما باید یه حلقه ثانویه ببنده رو سیستمتون که کار کنه. حالا اینی که من میگم حتما به اصطلاح چیزی بگیرید، من یه جوری میگم که اون کارو نکنید. بعضی جاها هم کار میکنه، یعنی ما 2 تا حلقه میبندیم، یه حلقه داخلی هم توش میبندیم، کار میکنه. ولی واقعیتش دقت کنید توی این داستان. موفق باشید. آرزوی توفیق بچه‌ها. خیلی طولانی شد کلاس، می‌خواستم ولی فکر می‌کنم خیلی عمیق بیشتر صحبت کردیم تا مفصل و امیدوارم که شما هم همینجور عمیق مطالب رو دنبال بکنید. آرزوی توفیق و سلامتی دارم. خدا نگهدارتون.
روز خوبی داشته باشید.